Hi, this unit is going to be on vector quantized variational autoencoders. And this is a model that has made very impressive progress in a lot of applications since it was introduced in 2018. So I'm going to start by contrasting the state of variational autoencoders in 2014, when they were mainly Gaussian, with what's happened since then. So this is a little bit unfair because I'm comparing 2014, 2019, but what we're looking at here is images generated from a variational autoencoder. If you take the prior and the decoder, that together defines a generator. I can sample from the prior and then sample from the decoding, and I get a sample from the distribution that is defined by the prior and the generator. So these are images generated from Gaussian in 2014. This is the state of the art in 2019. So this is now competitive with progressive GANs, generating extremely realistic people that do not exist. This is class conditioned modeling of ImageNet images. And so this is a dog that does not exist, but this is not a GAN, this is a VAE. And I'm convinced these are fundamentally different kinds of models, and I'll be talking about that more as we go on. The vector quantized VAE, the more recent versions, are multi-layer. So they're like a progressive GAN, where you're generating the generator, sampling from the prior, and then generating the image, is generating lower resolution images, then gradually higher resolution images, and then the final image. So it's similar to a progressive GAN in the structure of its generator. But I'm going to describe, for simplicity, at least in the beginning, just the single layer version, which appeared first. So the single layer generator, just to review what the generator is, what the model is this is an autoregressive prior over a symbolic image. And then we generate the symbolic image, and then these symbols are embedded. They have vectors associated with them. So from this symbolic image can be viewed as a layer in a neural net generator, and then we generate the image from that. I'm going to be talking about multi-layer versions in a separate unit. For this unit, I'm just going to focus on the single layer. And the single layer methodology gets used in, or very similar methodologies get used in the multi-layer case. So in this, in a VAE, we have an encoder, a prior and a decoder. So the VAE is going to take this image, and it's going to have an encoder that generates the latent information. And the way this is going to work is, the first thing we're going to do is we're going to take our image, and I'm going to use S as the image because I'm using Y as an image coordinate. So Y has been taken in this talk, so I'm using S for image. So I take my image S and I encode it via a convolutional neural network up to some layer of the convolutional neural network. Now, a layer of a convolutional neural network has image positions like pixels, but at each image position you have a vector. That's what a layer in a CNN looks like. So this is a layer. So I take my image, I pass it through a CNN, which I'm calling the encoder. I take a layer of the CNN. That's this layer has image coordinates, and at a given image place, it's got channel coordinates or feature or neuron coordinates. Now, what we're going to do intuitively is we're going to take the vectors. So here at a position XY, I've got a vector in this layer. I'm going to take the vectors in this layer at the various positions. And intuitively, what I'm going to do is apply K-means clustering. So I'm going to take each of these vectors and put it in some cluster. And that cluster is going to have a cluster center. That's what K-means clustering does. It divides the vectors into groups. For each group, it computes the mean of that group, which is the center of that cluster. And then the clustering algorithm is just you get assigned to the group whose mean is closest to you. Okay, so anyway, I'm going to do K-means clustering. Now, when I do K-means clustering, I'm not actually going to run K-means clustering. Instead, I'm going to have another parameter of the model, which consists of K mean vectors. So there's a table, and I can think of K, the cluster identity, the cluster index, as a kind of symbol, and I can think of the vector associated with that K as a kind of symbol embedding. So I personally like to think of this as a table of embedded symbols, where K is naming the symbol and I is its embedding. But you can also think of it as the centers of clusters, the center vectors of clusters. And now, so what I do is I take this image, I map it up to this layer using a normal convolutional neural network. And then what I'm going to do is I'm going to replace each vector by its nearest cluster center. So how does that work? So I've got this vector and I've got this table of embeddings, and I find the cluster, the K, whose vector is closest to the vector in this layer, right? So I'm taking I'm taking K to be the symbol whose center is closest to this vector. And then I replace this vector by the embedding of the symbol, right? So I'm going to call that L hat. L hat is what I get when I replace each vector by its cluster center. So this is just saying that L hat at XY is the cluster center of this nearest symbol. So this becomes the latent variable, right? This is a symbolic image. At each XY, it's got a K, which is a symbol. So now I can think of this as a symbolic image, and that is the latent variable of the VAE, of the variational autoencoder. Now, finally, for the model, we take this approximation, this conversion to the cluster centers, and we decode it. And we decode it back into an image. So that's the model. That's the variational autoencoder. We've got our encoder and our decoder, and I'll talk about the prior. We're going to train this in a two-phase fashion that's going to train the prior in a second phase. So in the unit on variational autoencoders, I talked about this two-phase optimization. And this is motivated by something called the autonomy of the encoder autonomy. So this is a simple observation in some sense. If in the first phase, I fix the prior to be some trivial thing, like in VQ-VAE, we're going to fix the prior in a first phase of training to just be uniform. And we're going to let the encoder be completely deterministic. So if we let so anyway, the two-phase approach in general is to fix the prior and then not to train the prior. We're just training the encoder and the decoder, but we'll train it according to the VAE objective, just for the fixed prior. And if you think about this, if you think of a stationary point of this, where everything is, the gradients of this objective are all zero, it means the gradient with respect to our decoder is zero. And the gradient with respect to the decoder is just this term, is just the gradient of this term. So the optimal value here satisfies this optimization problem. This optimization problem is just a cross entropy loss, right? It's saying that the decoder should model whatever this joint distribution is. So this, and if this is done well, it's sort of modeling the probability of the image given Z under this distribution, under whatever this distribution is. This distribution is defined by the encoder. And now in a second phase, I can train the prior just by sampling from this distribution and training a cross entropy loss onto Z. Now, if these two optimizations are done fully, completely and you've got universal expressiveness, it means that the model defined by the prior and the generator is exactly the model corresponding to this sampling distribution, or this sampling distribution where I've trained psi. And that will model the data exactly. It's modeling it under this distribution. So the idea here is that the encoder is sort of not as important as the prior and the decoder, because in principle, the prior and the decoder can perfectly model the data no matter what the encoder is. It just has to model the distribution that the encoder defines. And that motivates this two-phase training, or at least it can motivate this two-phase training, where this two-phase training can model the data exactly, even though the prior is trained later, right? So you can, in principle, you can model the data exactly by training the prior last. It does not have to be trained jointly with the encoder. And that's exactly what is done in VQ-VAEs. And it took me, I mean, I just now realized that there's this motivation for that architecture. And you don't really, you can argue at least that you don't have to train the prior jointly with the other components of the VAE model. So let's look at this in the particular case, or under the particular properties that the VQ-VAE architecture has. The VQ-VAE architecture is going to have a deterministic encoder, right? If you look, remember that encoding, it's just picking k, which is nearest to the vector. That's a deterministic step. So the probability of z given s is just 1. It's a deterministic computation, and I fixed the prior, and I fixed the prior to be uniform. So this is the same independent of z. So this term goes away, and the optimization is independent of this term. So the optimization just becomes how well have I reconstructed S, right? How well when I compute the encoding and then decoding, how well have I constructed S? And in a VAE with densities, you often think of that as this negative log density, but I've argued in previous units that negative log density is almost always thought of as a distortion, some kind of L2 distortion between the image that's given and the image that you reconstruct from the encoding. So you can almost think of this as like image compression, right? I compress the image into some encoding and then I decompress it and then I look at the distortion. Okay, now we've got a fundamental problem in that this argmin is not differentiable, right? This argmin is going to have some answer. And if I take a differential teeny weeny change in the parameters, that answer isn't going to change. So the gradient of the loss, this square loss, this image reconstruction loss, the gradient of that with respect to this symbolic image is 0. So it's really hard to backpropagate through this step. And VQ-VAE just has something that seems to work well for this optimization problem. And they combine what they call straight through gradients with what I'm calling Kmeans gradients. Because intuitively, I think it's intuitively correct to think of this as a K-means process. So what's happening here? The final image is computed from this L hat. And this L hat is this array of vectors, right? It's got a vector value, which is some mean of some cluster at each pixel position. But it's a nice numerical thing, right? It's got a vector at every position. So I can backpropagate the square loss back into this, right? So I've got L hat dot grad. What I'm having trouble with is backpropagating that into my symbol table and into the vector, the layer that was computed by the encoder. I have to train the encoder at the same time, right? So I have to get this gradient back into the encoder as well. So I have to go back from this gradient, which I can get, back into this. And I'm just writing the equations that are used in the paper. So they take this gradient, one component of it is they take this gradient and they just apply it to the input, the thing that was quantized. Now that's going to be meaningful if these two are close, right? If this move to the center is not a big move, then the gradient here should be roughly equal to the gradient there. The gradient here, if I just pass this through to the decoder, would be similar to the gradient here. But that assumes that these are close. So to make this work, to make this straight through gradient work, you need them to be close. So you add another term, intuitively another loss term that drives them to be close. And that's the K-means objective. So the other thing I do is I push on the vector that was computed by the encoder to make it closer to its center. I want the encoder to move closer to its center, to make these close. And the other thing is I want the table of embeddings to move closer to the encoding. So this is the only gradient on the table of embeddings. And the only gradient on the table of embeddings is moving it closer to the vectors that were in that cluster, right? Because this is only going to happen, this is the sum over the vectors in the cluster. For every vector in the cluster, I move the cluster center toward that vector. A stationary point of this training algorithm has the property that this will be exactly the mean. This objective has the property that a stationary point will make this exactly the mean of these, right? If I just set this to 0, that's exactly what I get. This has to be the mean of these, which is exactly what you get in K-means clustering. So a stationary point of this achieves a K-means clustering of the vectors in this layer. Okay, I fixed, when I did this is phase 1. I fixed the prior to be trivial, uniform, right? And I'm ignoring it. But the prior is an important part of the model. So then there's a phase 2 in this. Now we've got we've got an encoder. We've trained the encoder and the decoder, boom, boom, but we haven't trained the prior. We took the prior to be trivial, uniform. But since we've got an encoder, now I've got, if I sample images, I'm sampling these symbolic images also, because I've got an encoder that takes the image to a symbolic image. So since I can sample these symbolic images, I can train an autoregressive model of this symbolic image. I just predict one symbol at a time autoregressively. I can do a raster scan, or I can do some other order. And so I train an autoregressive symbolic model of the distribution over these symbolic images. And now I can now an autoregressive language model can be sampled from, right? So I can sample one of these from the prior and then generate the image by the generator. Okay, so I've skipped over the multi-layer case. I'm going to talk about that in a separate unit, about my take on multi-layer in a separate unit. But now I'm just going to talk about some empirical results from the VQ-VAE2 paper. So this weird, what I'm about to describe is a kind of weird experiment. We can generate images from the VQ-VAE. We train a class conditional VQ-VAE for dogs, and for cats, and for fish, and for any class, right? So we've got all these class conditional VQ-VAEs, so we can take our class conditional VAE for dogs and generate dogs. We can take the one for cats and generate cats, and so on. And if I do that generation, I get a set of labeled images. I label the image that was generated from the dog VAE as a dog, and so on, right? So I've got a set of labeled images. Now I can train a classifier, your favorite classifier, say ResNet, on labeled images. I'm just training it as a classifier, and I've got a corpus of labeled images, but the corpus of labeled images is all fakes, right? It's all things that were generated from this VAE generator. So I train a classifier on fakes. And then I can take the actual ImageNet data, test data, and evaluate how well it actually classifies actual ImageNet images. Okay, so trained on fakes, but tested on real for classification. So now they're comparing so now we can take various systems and say, and we have top 1 accuracy and top 5 accuracy. Let me try to explain that. Top 1 accuracy means you take the most likely label and is it right or wrong? And if it's right, then you get it right. Top 5 accuracy means you take the 5 most likely labels, and if the true label is one of the 5 most likely, then you get it right. So that's the top 5 accuracies. So the top 5, that's an easier problem. So these accuracies are higher. So now what they're comparing is big GAN is the GAN, the big GAN that was doing really well. One of the at the time this paper was published, that was the leading ImageNet GAN, class conditional ImageNet GAN. And it does not do as well on this particular test as the VQ-VAE. So this is a different performance test for a GAN from inception score, or there's this problem of how do you evaluate generators. If you just have a generator, how do you evaluate it? Now this, I believe, and I still haven't looked it up, I believe that this reconstructing means you take the images, the fakes, and you make them more real by just changing a few statistics. You make the color balance right, you make the contrast right. So just by reconstructing the image in some trivial way to make it match the statistics of the real data, they get a little bit better score. And now if you take that same ResNet that you're training on the fake training corpus, and you train it on the real training corpus, it does better. But it's kind of surprising that you can take this fake data and produce a classifier that does quite well, not that much worse than training on real data. This VQ-VAE2 has multiple layers. Here you've got 3 layers. And this is, so you generate an image by generating symbolic images of increasing resolution. What you can do is you can take that first image and generate the lowest resolution image you generate, the top layer, and you can generate the image directly from that. Or you can do the top and middle and generate the image, or you can do all 3 and generate the image. So what they're doing is they're taking the original, they're using the encoder to get all of those layers, right? The encoder will give you those lower resolution images, and then you are generating the image back either just from the top, or from the top 2, or from the top 3. And that's what we're seeing here. So you can think of this as a kind of image compression. You can also do a direct rate distortion evaluation. Now, I'm not very happy with the numbers they report here. I believe these are the negative log likelihoods of those autoregressive models measured as language models. What's the negative log likelihood of the probability of the next symbol? That's the way you would evaluate a language model. And then there's this mean squared error, the difference between the reconstructed image and the given image. And something to note here is that in their experiments, the reconstructed error is really negligible. That sort of corresponds to these images being, essentially identical. So they've built this system such that if you encode and decode, you get it's lossless. It's essentially a lossless compression algorithm. I would love to see a better number here, which is bits per pixel, which is which is a standard measure for image compression, and that would really be I'm not sure exactly what these numbers mean, but I would like to see this in bits per pixel. Okay, I've talked about DALI before as one of the things that's happened in the most recent year. And this is basically a vector quantized VAE, except now instead of being class conditional, it's text conditional. So you take an enormous corpus, which you can get from captioned images on the web, or the language put on hypertext links. You get an enormous corpus of images paired with text. And then I want to have a conditional probability model of the of the image given the text. And in a VQ-VAE, you're converting that image into a symbolic image, an image of symbols. So I can use a standard language model that reads the text and then it reads the text and it sees a special token, and then it reads the image as a sequence of symbols. But it's just a language model. It's just looking at a sequence of symbols over the text, then a sequence of symbols for the image. And that language model can be used to read text and then generate the image. And you can get really shocking images. An illustration of a baby daikon radish in a tutu walking a dog. These are different samples of different images generated from that text. And an armchair in the shape of an avocado. Now, these are cherry picked, right? It's not always going to do this well, but the idea that this can be done at all, that it gets any images that are this good, I find really shocking. And I just want to say it's really important to keep in mind the difference in which the different ways in which the VAE, the difference between a VAE and a GAN. A GAN is trained to fool a discriminator. A VAE is trained to take a real image input and model it, model the distribution over real image inputs. And our experience with language modeling, for example, is this idea that actually modeling the real distribution, looking at the distribution and modeling the samples, gives you a more useful system. The GAN, this is my anti-GAN spiel. A GAN can fool the discriminator by having a very sparse representation of what it actually generates. Even in style GANs, you can identify an image that's been generated by a style GAN from real images by seeing whether the style GAN has a random variable that will generate that image. And a real image will typically not be something the GAN can generate well, whereas a VAE is trained to be able to generate any sampled image from the space of images. So I think that's an important distinction between GANs and VAEs. And I'll end there.